Hello everyone and welcome to this lecture. In the last lecture we have seen introduction of some matrices like incidence matrix, then Laplacian matrix, and these displays very simple and good looking properties. Okay, but motivation was something else. Why we actually introduced these matrices? Motivation was proving that in a given connected graph, the number of spanning trees can be given by the any cofactor of the Laplacian matrix. We have to prove it. Journey is still the proof is still far, and I gave you one disclaimer in the beginning of the last lecture that the journey is actually not very difficult. Okay, it's actually, if you know the 11th or 12th class, this determinant properties and all that we learned in 11th and 12th class, you will easily grasp this, but the things are slightly counterintuitive. Okay, today in this lecture we will prove that when we select n-1 edges from a graph having n vertices, whether these edges will form a spanning tree or not. Remember that in a tree on n vertices it will have n-1 edges, right? So if it has to be spanning trees, it has on a graph having n vertices, this will have n-1 edges, right? So today we will see a kind of deciding thing that will tell whether n-1 chosen edges will form a spanning tree or not. So let me start with the lecture, and before actually giving you the main deciding factor, I will have to use some notation. The notation is this: suppose A is your n cross m matrix, okay, and suppose S is some subset of numbers from 1 to up to n, okay, and then and then T is another subset, which is subset of the set of numbers from 1 to up to m, okay. Then notation is okay, is this. Suppose this notice, by this I will we mean this, the submatrix of the submatrix of A, where let me write it here, where the basically rows are indexed by the elements in S, okay. Basically whatever the elements in S are, those rows we will pick from rows of A, and similarly, and columns are indexed by elements in T. Very good. And similarly I will define, will use this notation T by the submatrix of A, where the columns are, where the rows are not indexed by the element in N, and similarly columns are not indexed by the element in. So AST is the submatrix of A, where the rows are not indexed by, where or maybe more clearly, where the rows are indexed by the elements not in S, and columns are indexed by the elements not in T. Okay, very simple. So let me give you one example of it so that the notations are clear. Okay, suppose A is equal to 3 cross 3 matrix, some 1 0 5 2 minus 7 2 1 0 2. Okay, so suppose your S is 1 3 and your T is maybe let's say 2 3. Okay, so what will be your AST? AST is nothing but this, right? AST will be what? The rows are indexed by 1 and 3, so 1 this and 3, and then 2 and 3 are the column. So basically this, so it will be a 2 cross 2 matrix with 0 5. Hopefully I'm doing it correctly. Yeah, 2 3 and yeah, very good. Yeah, very good. And similarly you can see about this notation. Okay, very good. Now let me say one of the most beautiful result for this lecture. This lecture tells this theorem tells that okay, suppose you have a graph on n nodes, connected graph on n. Suppose let G be a connected graph on n vertices and m edges. Suppose these edges are E1, E2 up to EM. Okay, let S be the subset. Let S be a subset of numbers from 1 to up to M. Okay, M, and with having, or maybe I would use the word here T here because I will be using column shortly. So where the cardinality of T is basically element in T are n minus 1. Okay, okay. Let H be the subgraph, be the subgraph on the edges whose indices are in T. In fact, T only I will to move, so there are no other edges whose indices are T. Then what? H will form. H is an spanning tree if and only if, okay, the statement looks very vague, but the result is, it's a very, very simple one. Okay, it says that the H will form a spanning tree if and only if the determinant of, now here the determinant thing all of a sudden comes, the determinant of submatrix of incident matrix. And let me tell you what is that submatrix. You choose n minus 1 rows, okay, n minus 1 rows, 1 2 up to n minus 1. So these are rows. Okay, ideally you can choose any n minus 1 row, so I am by default choosing first n minus rows, and then choose columns corresponding to T, whatever T, right? You basically T is what the corresponding to edges, n minus 1 edges you are choosing. If those n minus 1 edges are forming a spanning tree, then so basically this is okay, equal to plus 1 or minus 1. Okay, determinant of this matrix will be H is spanning tree if and only if, okay, this happens. Okay, very, very good. So this tells this. So let me write the proof of it, but before proving, let me actually give what we mean by this statement. Suppose the graph is same, right? So graph is same. Suppose this one. Okay, now there are 4 vertices and you have to choose 3 edges, right? Because n minus 1 edges. So it says that suppose you are choosing these edges. Of course, these are not forming a spanning tree. They are not forming, in fact, forming a tree at all, right? So it says that if you choose these edges, they are not forming a spanning tree. Then if you see the incident matrix of this graph, we have already seen whatever incident matrix depending upon the edges. Okay, you see the columns, rows 1 2 3 and the columns corresponding to these chosen edges. Remember E1 E2 E3 whatever name you give. Okay, and then this 3 cross 3 matrix will give you determinant 0 in this case. Okay, 3 cross 3 matrix. Okay, now let us prove in general. Okay, so we will prove first the case. We will prove the first case that these chosen n-1 edges, basically the subgraph H is not forming a spanning tree. Okay, the first case is, suppose the chosen, the selected n-1 edges are not forming a spanning tree. I hope, yeah, correct. A spanning tree, that means H is, yeah, so H is not a spanning. H is not, I will write a short form, not a spanning tree. I mean, this can be, this is possible in two cases. If you see, maybe these n-1 chosen edges are not spanning at all. Okay. Or they may be spanning, but they are not forming a tree. Okay. So let us take both of these cases. H is not spanning at all. So maybe H is not spanning. Is spanning at all. Okay. Spanning at all. For example, let us take the same graph here. So here, suppose this one. Okay. Okay. Maybe I can take a slightly bigger one also. Okay. So how many vertices are there now? There are 6 vertices, and let us take some 5 edges. Okay. So suppose take these 5 edges. 1, 2, and then 3, 4, and 5. Okay. Now you see that these edges, the red ones, these selected n-1 edges are not spanning, right? In this case, what will happen? There will be at least one vertex which is not falling on these red edges, chosen edges, right? So this is kind of for this H, inside H, this H is made up of these reds. So there is a subgraph, there is a vertex which is not at all incident on these red edges. Okay. So how your incident matrix will look like? So let me write the incident matrix here. Incident matrix will be this, right? I am actually labeling these red edges as E1, E2, En by default. So E1, E2, En-1 because they are n-1, and then E1, En, and so on up to En. Okay, and we have to talk about this submatrix. So this is 1, 2 up to n-1. Okay, by default I can assume that the nth vertex is not at all incident on those edges, right? On those red edges. Suppose this is the last vertex. Okay, now you see that all these edges there will be zeros because these edges are not at all incident on, and rest of the places here there will be somewhere 1, there will be -1, and 0, 0, and so on, right? 1, -1. This is ideally incidence matrix of H. This part is incident matrix of H. But we have seen in the last lecture, if you pick any column, there are only 1 and -1, right? And rest of the entries are 0. So if you add this will give you 0. In the similar way, if you add individual all columns, right, it will give you what? It will give you 0. And then by the simple determinant properties, linear combination, or maybe just add all these rows, it will give you what? So this add this, this will give you a 0 vector. And so the determinant of this matrix will be determinant of this part. I will just remember this is equal to 0. Very, very easy to see because we are adding all this, right? So R1, R2, R2, Rn, and this will, if you add all this will give you 0 vector. Very good. So very, very simple fact. Now let us see the another case. What? Okay, so another case is suppose this B1. Okay, so B is what? In that case, suppose H is spanning, but it is not forming a tree. Okay, so this is the case. H is spanning. Okay, it is covering all the vertex. It is spanning. Spanning is mistake. Basically, those chosen n-1 edges are spanning or covering all the vertex is spanning, but not a tree. But not a tree. In this case, what will happen? Let us see. Let us again draw a graph. Okay. So suppose this is, okay, and let me let me, maybe augment more, so maybe I can write something. Sometime I'm making, yes, these are vertices, and then maybe this. Okay. Now, how many vertices are there? Are 8 vertices, so I have to choose n minus 1 edges. Okay. So let me choose this such that all these edges actually are covering, maybe one more here, same graph, such that all these edges are covering all these vertices. Okay. So let me start with this. So this is covering all this. So maybe this one. Okay. So E1, E2, and then how many? So let me actually first. Okay. So why not I do this? So this vertex is covered. These two. This is also covered. This is also covered. Every vertex is covered. But are we? So how many vertex were there? Are 8. But how many edges I have chosen? Is still 3, 5. So I have to choose 2 more, right? 2 more. So maybe I can choose this. Oh, maybe I can choose this. Very good. So how many edges? So there were 8 vertices, and I have already chosen 7 edges. Okay. Now, if you see that in this case, remember I gave you in the first lecture itself, there was a one DIY, do it yourself exercise, that suppose you have a graph on n vertices, okay, and in that graph there are only n minus 1 edges, and suppose this is not a tree. Suppose this is not a tree. In this case, there will be at least 2 components. Just look at this graph on red ones, right? Red. How many connected components are there? There are 3 connected components. So this is first one, C1. This is another C2. This is 3 on red ones. Just look at the red, right? In this case, again, now you see that when in this case there will be at least 2 components. Let me define, let us choose this component C1. Okay, so how your incident matrix will look like here. Incident matrix will be something like this, right? Suppose these edges are corresponding to C1, these edges are E1, E2 up to EP, E1 up to E2 up to EP. Then there are edges of other components, EP1, and so on. And maybe then other components. So these are, suppose this is component 1. These are edges of component 2, and so on. Okay, component. Suppose there are CK component, and then there are rest of the edges. Okay, dot dot dot. Then there are rest of the edges. Okay, so maybe I can write that these are rest of the edges. Rest of the edges. Okay, very good. Now, if you see what? Okay. Let us try to see what will be the incident matrix in this case. These edges, and let me write the corresponding here vertices. So suppose 1, 2 up to some number here. Okay, and some number. Okay, so if you some number is, suppose I am not care about what that number will be, but if you see whatever these vertices will be, those are incident on these red ones here. These vertices are not at all incident on rest of the components. So all the places this will be zeros. Okay. So whatever the vertices here, suppose this vertices is, maybe I can tell what whatever name, maybe up to suppose D number of vertices are there here, right? So these vertices here, these vertices are not at all incident on the edges of other component. Okay, so this part will be 0. Now what? What about the entries here? Now remember, these edges are also not incident on the vertex of other components or other vertices. So these vertices will be what? So these entries will be also 0. Okay. In this way, you can do the same thing for other component. Like suppose this one, right? Again, there will be some basically this vertices will be, there will be some vertices corresponding to C2. So this will be some +1 and -1 here. So again here there will be 1 and there will be -1. Rest of the value there will be 0, right? 1 -1. Okay. And similarly, other place it will be 0. Similarly here it will be 0. The picture will look like this. So there will be incidence, submatrix of incident matrix corresponding to the column, the component 1, then component 2, then component K, and till here all these your n minus 1 edges will be consumed by these components, all the components, okay, and these will be the n minus 1 your vertices, okay. Now and everywhere there is 0, okay. Now if you add all these rows, or basically now we have already seen the properties of incident matrix, right? You pick any column, all the entries, if you add, this will give you 0. So indeed, if you add all these things, stuff here, this will give you 0. In fact, you start from here, start from all this, keep on adding all these rows, this will give you a 0 vector again, 0 vector, big 0 vector, okay. And this again will give you determinant 0. Determinant of, the matrices, the desired matrix is equal to 0, okay. Very good. Very, very good. Now the trickiest part is the case when H is forming a spanning tree. So second case is H is an spanning tree. Spanning tree, again I am making mistake in writing, spanning tree. Why in that case determinant will be either +1 or -1, okay. Think about it. You can I can pause this video and then you will realize, why in this case it is coming out to be 0, and what is so special in the case when spanning tree is H is a spanning tree, and why only this 1 and -1, why not other number? So very, very beautiful fact, okay. So let me prove it, okay. So suppose you have a graph, this graph, and H is this, H is inside this graph, there is this H, right? Very good, and so on. Very good. So now if you see, so this is a tree, right? This H is forming a spanning tree basically, okay. Now I remember in the again DIY of the first lecture, I gave you this question. If there is a tree on n vertices, where suppose n is greater or equal to 2, there is always at least 2 pendant vertex or at least 1 pendant edge, right? Okay, so you can go back to the definition of pendant. Pendant vertex is a vertex which is having the degree 1, okay. So we will make a beautiful use of these pendant vertices, okay, to form with submatrix corresponding to Qs in very beautiful way, and then the result is apparent, okay. So suppose this is incident matrix of your QZ, okay, and by default let me number these columns using first these red ones, right? The edges, chosen edges. Suppose this is E1, E2 and so on, okay. But I will do this very, very cunningly, okay. I will choose a vertex having degree 1. Basically I will choose a pendant vertex. So how many, there are many pendant vertices, for example here. So let me choose this one and I will call it 1. Suppose this is 1 vertex, and the edge which is incident on 1, I will call it E1, okay. So what will be the corresponding entry in the in my QZ? It will be either +1 or -1 depending upon the direction I am giving to this edge, right? Either +1 or -1, okay. Now what I will do, I will ignore this edge and then this vertex 1 and E1. The resulting graph, you assume that these two guys are not here, right? The resulting graph is still a tree, okay. Again you will get a pendant vertex, okay. Suppose that another pendant vertex is this 2, okay, and the corresponding edge I will tell E2, and depending upon the edge I will the direction of edge it will be, so this is E2. Here the entry will be on 2, it will be +1 or -1. What about the entry this? What about the entry? This will be 100% 0 because E2 cannot fall on 1, right? So this will be 0. Now let us take one more and then the picture will be clear. Now what we can do is now again you ignore like 1 and E1, now ignore also 2 and E2, right? The resulting graph will be again a tree. Now you will get another pendant vertex, okay. So suppose this pendant vertex is maybe this is also pendant vertex, right? Because your E1 is not there anymore. E1 and 1 vertex is not there anymore. So this will also become a pendant vertex in the third step. So this is suppose 3, okay. So this is your E3, Okay, and then you can write this. What will be this entry? This entry is nothing but plus 1 minus 1. But what about 1 and 2? These will be 100% 0 because E3 cannot fall on vertex 1 and 2. Okay, in the similar way, you keep on going till n minus 1 edges. Okay, you will always get the till n minus 1 vertex. Okay, this plus minus 1 stuff. Okay, dot dot dot, everywhere here it will be 0. Okay, and rest of the places this will be plus 1 or minus 1, depend here, maybe plus 1 or minus 1. Okay, 1 minus 1. Okay, zeros. Okay, so this matrix, if you see that, this matrix is nothing but this matrix. If you see this part, right, this is an what, a lower triangular matrix. So we have to actually see that on the above the diagonal everything is 0. What will be the determinant of such matrix? The determinant nothing but product of its diagonal entries. Okay, so the determinant of this matrix, this bigger matrix, is nothing but product of plus 1s and minus 1s. Okay, so the determinant of, basically in this case, determinant of, let me write with white color. So determinant again in this case of QG, where you are selecting n minus 1 rows. Okay, and the columns corresponding to the T, right, basically n minus 1 edges chosen. If they are forming a spanning tree, this will give you the determinant either plus 1 or minus 1. This is a very, very beautiful fact. Maybe at first glance it looks counterintuitive, but very, very simple one. Okay, please go through it again. Next lecture we will see a very, very good application of it. In fact, in just one step, we will prove that matrix tree theorem is nothing but cofactor. Any cofactor of Laplacian matrix will give you the number of a spanning tree, and you already know Laplacian matrix is related to incident matrix. So there is a very beautiful connection with this result, and the result we will see in the next result, next lecture. Till then, thank you very much. Yeah.